Hello everybody. Today we are going to have the last lecture on this Unit 2, which is devoted, as you know, to context-free languages. Okay, so in the last lecture, we introduced the idea of push-down automata, which are the machines that we can use in order to check if a string is in a context-free language or not. Okay, so you may be wondering whether there are different types of push-down automata, as there were different types of finite automata. Remember that in Unit 1 we studied deterministic, non-deterministic, and non-deterministic with lambda moves finite automata. But in this unit, in the last lecture, we introduced push-down automata directly as machines which have both lambda moves and non-deterministic choices. Okay, so you may be wondering if it is possible to define deterministic push-down automata, and in that case, whether they are equivalent or not to the push-down automata that we have defined. And the answer is that yes, we can define deterministic push-down automata, but they happen to be non-equivalent um, to the non-deterministic push-down automata. Okay, at least when we accept languages by empty stack. Okay, so we are going to define today what we understand by deterministic finite automata, push-down automata, and we are going to show that there are certain languages that we cannot accept with deterministic push-down automata, but we can accept with non-deterministic push-down automata. Okay, so the idea is that when we have deterministic finite push-down automata, we cannot have different choices when we are scanning a word. Okay, so that is exactly the same idea that we had with finite automata, in which whenever we were computing with a word, we were processing a word, we always had one and just one choice for the new state of the machine. Here, in push-down automata, in order to have determinism, we again need to have just one choice for each possible situation in the computation of the automaton. So this implies that for a push-down automaton to be deterministic, it has to verify two conditions. The first condition is that for all states and for all symbols in the alphabet stack, and for all symbols in the tape alphabet, we cannot have at the same time a lambda move like this one here and a move with a symbol of the tape. Okay, so if we had at the same time for the same state and the same symbol in the stack two different possibilities, one with lambda and the other one with a symbol in the tape, then we could have different choices at a given time. Okay, so this is not possible. We cannot have a move at the same time with lambda and with a symbol in the tape. Okay, so for instance, an automaton with these transitions here would be non-deterministic. This would be non-deterministic. Okay, because if I'm in a state Q and at the top of the stack I have symbol A and in the tape I have B, then I can either make this transition using the symbol in the tape, or I can make this transition with lambda. Okay, so that would make the the automaton non-deterministic. Okay, so this kind of situation is completely forbidden when we have a deterministic automaton. Okay, so this is one of the two conditions that an automaton must verify. We cannot have possibilities like this. Okay, the other condition is that all the transitions in the automaton will have at most one possibility. Okay, so the size of the set that the machine returns for a given possibility must be at most one. Okay, so again, a situation like this one shown here is non-deterministic. Okay, this is non-deterministic because we have this possibility and this possibility. So if I'm in a state Q, at the top of the stack I have S and I have A on the tape, I can choose between doing this transition or doing this transition. And then I have non-determinism. Okay, so of course this is a possibility that is not allowed when we have a deterministic automaton. So in order to check whether an automaton is deterministic or not, we must check whether there are situations like this one here. Okay, and if we find something like that, then the automaton is non-deterministic. And we also must check whether we have situations like this one here. And if we find any situation like this, then the automaton is non-deterministic. Okay, so uh, let me give you an example of a language that can be accepted with a deterministic pushdown automaton. But if we modify slightly the language, then it cannot be accepted by an automaton which is deterministic. Okay, so the idea is to consider this language here in which we have words which are somehow symmetric. We have first a part set which is composed of zeros and ones, then we have a 2, and then we have set reverse. This set to the power r is the reverse of the set of the string set. So imagine that set is 110, for instance, then set r is the reverse, is the string read in the other direction, so it is 011. So the words that are in this language are those of the form, for instance, 11012, and then the reverse of this part, 1011. Okay, so we have a first part, then a separator, which is a 2 in this case, and then we have the same string that we had at the beginning, but read in the other direction. Okay, so what we are going to do is to use a deterministic pushdown automaton in order to recognize, to accept the words in this language. And what we are going to do is to use, of course, as tape alphabet 0, 1, and 2. Those are the symbols with which we write the words of the language. We are going to use as the stack alphabet Z, which is the initial symbol of the stack, and then a C to denote that we have read a 0, and a U to denote that we have read a 1. Okay, and we are going to have two different states. One, P, in which we are reading the first part of the word before the 2, before the separator, then Q, which is the state that we are going to use when we read the 2, okay, when we read the separator. The initial state is going to be P, because at the beginning we are going to be before the separator, before the 2, and we are going to use the automaton to accept words by empty stack. So that's why the set of accept states is empty. We don't need to know what is the set of acceptance states, because we are going to accept words by empty stack and not by final states. Okay? And the transition function uses an idea similar to the one that we used in order to recognize uh, the words of the form a n bn. Okay, so in the first part of the word, we are going to use the stack to store symbols which denote the different elements, the different symbols that we have read in the first part of the word. And then in the second part of the word, when we uh, read the separator and we move into state Q, we are going to pop those symbols in order to check whether they are exactly the same symbols that we are finding now in the tape. Okay, so since we have a stack, the order in which we recover, in which we pop the elements, will be the reverse of the order in which we introduce them, and that's why we can find out whether the second part of the word is the reverse of the first part, because we are going to store the symbols of the first part and the stack is going to reverse them for us. Okay, and then when we pop them, we can check those symbols against the second part of the word. Okay, so these first transitions here are the ones that we are going to use at the very beginning, when we have on top of the stack the initial symbol of the stack. Notice that we are in state P, which is the initial state, and we have the initial symbol of the stack on top of the stack. Okay, so we are at the very beginning, and when we read a 0, we store a C on the stack. When we read a 1, we store a U on the stack. And another possibility is that we directly at the very beginning read a 2, and this means that uh, the word here is lambda. Okay, so in that case we directly change into a state Q, and we do not store anything on the stack, because we have read nothing. We have no symbols in the first part of the word. Okay, now when we have already stored at least one symbol in the stack, and we are still in state P, we can read a 0 after having read a 0, a 1 after having read a 1, and in those cases we just store the same symbol twice. Okay, we remember that we pop out the symbol from the top of the stack, so we pop out this C here, and since we have read another 0, we need to push in the stack two C's. Okay, for the C that we have popped and for the new 0 that we have read. And when we read a 1 after a 1, we do exactly the same. We store two U's on the stack, because we have popped one U and now we have read a new one, so we need to push two ones on two U's on the stack. Okay, we can also read a different symbol uh, after we have read a 0 or a 1. So after a 1, for instance, we can find a 0, or after a 0 we can find a 1. In that case, we store the two elements in order. Okay, in this case we have popped the U, and we need to push the U and the new 0, and in this case we have popped the C, and then we need to push the C and the new 1. Okay, that's why we have two symbols again here. Next, we are going to find the middle of the string. The middle of the string is found when on the tape we have a 2. That is the separator between the first part of the string and the second part of the string. In that case, notice that what we do is to change the state. We change into state Q. Remember that Q is used to pop symbols from the stack, and it means that we are already in the second part of the string. Okay, so when we read the 2, we change nothing on in the stack. Notice that we pop the U, but we push it back again. We pop the C, but we push it back again. But what we do is to change the state Q, the state of the machine into the state Q. Okay? And then when we are in the second half of the word, we need to check whether the symbols that we have on the tape, a 1 or a 0, are exactly the same symbols that we read in the position, in the mirror position in the first part of the string. So when we read a 1 on the tape, we expect to find a U on the top of the stack. When we read a 0 on the tape, we expect to find a C on the stack. Okay? And in that case, we do not change the state, but we pop the symbol. We push back lambda. It means that we do not push anything back onto the stack, and the overall change in the stack is the pop of the symbol U or C, depending on what we have read. Okay. Finally, at the end, we are going to find the initial symbol of the stack. When we pop back all the symbols in from the stack, all the symbols that we have pushed when we were reading the first part of the word, when we push all those symbols out of the stack, we are going to find the initial symbol of the stack. In that situation, without reading anything from the tape, we pop the initial symbol of the stack in order to make the stack completely empty. If at this moment we have read all the symbols on the tape, we have read the complete word, then we are going to accept. Okay, because remember that we are using this automaton as an automaton that accepts by means of empty stack. Okay, so these are the transitions of the automaton, and notice that this automaton is indeed deterministic, because all the sizes of all the transitions here are 1, 1, 1, 1, 1. All of them are 1. Okay. Also here 1, 1, 1, size 1. And finally here all the sizes of the transitions are 1. Okay. So this is one of the conditions that we need to meet in order for the machine to be deterministic. The other condition is that whenever we have a lambda movement, like this one here, we cannot have at the same time a movement with a symbol. Okay, so we cannot have, for instance, a transition for Q, 0 and Z, or for F, Q1, 0Z, or F, Q2, Z. Those cannot exist if we want the machine to be deterministic. But if we take a look at the transitions, we quickly notice that there are no transitions of that type. Okay, there is here a set of transitions with 0 and Z, but they are for state P. for state Q, the only transitions that we have are the ones on this slide, and they are not for Q0 set or Q1 set or Q2 set. Okay, so both conditions are met, and this automaton is deterministic. Okay, let's see with an example how this automaton works on a given string. Okay, so for instance, imagine that we have um, a simple string like um, 0, 0, well, no, let me say 0, 1, 2, 1, 0. Okay, so at the very beginning we are in state P, and we have set on top of the stack. Okay, so the next transition will be, if you remember the movements of the transition function in the automaton, we have P0 set. What we do is we stay in P and we accumulate the 0 on top of the stack. So here we have a C. Now we have P1 C, and what we do is to stay in P, and then we add a U to the stack. Remember that we pop the C, but then we push back the C and the U. Okay? Now we are in a situation in which we have 2 on the tape, so we change into Q without, we read the 2, but we do not change the content of the stack. And then when we are in state Q, we check whether the symbol in the stack and the symbol in the tape are exactly the same. In this case they are, and then we begin popping these symbols. So here we go to Q0 C set. Again, this is exactly the same, so we have Q lambda set, and then we use the lambda movement in order to empty the stack. And since we have already read all the symbols on the tape, it means that the word is accepted. Okay, so notice that here, of course, this word is part of the language and it is accepted. Also notice that at all the movements here, we only had one possibility because the automaton is deterministic. Okay, you can try with other words and you have a similar behavior. Okay. Then this is a deterministic automaton that accepts this language of words with a separator in the middle, and then the reverse of the first part of the string on after that separator. Okay. Let's see what happens if we remove the separator. Now the words are very similar. They are of the form set reverse, so we could have here words like 0, 1, 1, and then 1, 1, 0, for instance, but we have no separator. Okay, and now the problem is that if we try to do something similar to what we did with the previous automaton, there are times in which we are not going to know what to do. Maybe we have several different options because we are missing the separator. The previous automaton was deterministic because we always knew whether we were in the first part of the word or in the second part of the word, and that was marked by having read or not having read the separator. But here, what is the equivalent of the separator? Well, we could have a mark of the middle of the string when we have two symbols that are exactly the same. So here, for instance, when we are at the middle of the string, here we have two ones, uh, consecutive ones. Okay, but notice that also here we have two consecutive ones, and that is not the middle of the string. So for a word of this language, if we find two consecutive ones, that is not sufficient condition to know that it is the middle of the string. It is a necessary condition. If we are at the middle of the string, we need to have two different, the same symbol twice. But if we have the same symbol twice, it does not mean always that we are at the middle of the string. And this is going to affect the way in which we make the movements in this automaton. Okay, so the beginning is very similar. Here we have two transitions which are exactly the same as in the case of the deterministic automaton. Also, we have transitions which are very similar, so or exactly the same. For instance, well, this transition is repeated. Please do not pay attention to it. This is repeated, but these transitions here are exactly the same as in the case of the deterministic automaton. Okay, because in this case we find two different symbols, one after the other, so we know that for sure we are not in the middle of the string. Okay, the problem is that when we find two symbols that uh, are equal, when we find two consecutive symbols that are equal, then we do not know whether we are at the middle of the string or not. Okay, and since we need to explore all possibilities, we need to branch the computation. We need non-determinism. Notice here that this automaton is non-deterministic because these transitions have length 2. Okay, so at this point we have two different possibilities. Okay, and then what we do here is if we find a 0 after having read a 0 or a 1 after having read a 1, we uh, do not know what is the real situation. We do not know whether we are at the middle of the string or not. So we need to explore both possibilities. This is the possibility of not the middle of the string. So then what we do is to stay in P, and this is the possibility of being at the middle of the string, and we have to explore both possibilities. Okay, then after that we have exactly the same behavior as we had in the deterministic automaton, because now we only need to check whether the symbols after we have read we have reached the middle of the string are exactly the same symbols as the ones that we had in the first part of the string. Okay, so this is exactly the same. You can check that these transitions are the ones that we had in the deterministic automaton. Okay, so the difference is with these transitions, which are non-deterministic, and also with this transition here, which is the equivalent of what we had when we read the separator just at the very beginning. Okay, because when we read the separator at the very beginning, it meant that the first part of the word was lambda, and then we need to change directly into the second part because we have read the separator. So here, if we read lambda directly, if the word is lambda, we need to change directly into the second part of the word, okay, for being able to accept lambda. And notice that this transition here also makes the automaton non-deterministic, because when we are in this situation, we can have a movement with either the symbol 0 or with lambda, or with the symbol 1 or with lambda. So again, this makes the automaton non-deterministic. Okay, so this is an automaton that is non-deterministic because it does not meet any of the two conditions. It is sufficient not to meet one of them for the automaton to be non-deterministic, but in this case, we do not meet neither of the two conditions. Okay, so this is non-deterministic because of because of any of those violations of the rules. Okay, so let's see how this automaton works on a small string. For instance, let me create here um, a new slide, and let's say that we try to see what happens with a word like 01110. Okay, so again we start with set as the only symbol in the stack, and we start in state P. But now at this moment we have two possibilities. We can either use the lambda move to go to Q, or we can stay in P and read the symbol 0. Okay. Notice that in the right branch, then after this we cannot move anymore. Well, yeah, we can move, but we are going to empty the stack. Okay, this is the only possibility here. And when we empty the stack, since we have not read the word completely, we are not going to accept. So in this case, this branch does not lead to acceptance of the word. So we have this possibility here. And in this possibility, now we can only move to stay in P and then accumulate the one on top of the stack. Okay? But now we have two symbols, two consecutive symbols that are exactly the same. So we have two possibilities. The first possibility is to stay in P, and then we accumulate another one on top, or we move to the second part of the word, or we decide that we are in the second part of the word, and we start removing symbols. Okay, so here we are going to have the 0, we are going to have the rest of the stack, but we have popped the U out of the stack. Okay, you can check that from here you can make more moves, but it won't lead to accept the word. You can do that as an exercise. And here notice that now we consume the 0, and then we empty the stack. Okay, so with this branch we accept the word. But notice that the automaton is non-deterministic because we have several branches and only one of them is accepting. Okay, so this is different from what we had with the deterministic automaton, in which we had a linear sequence of movements. Here we have a tree of movements, and one of them is the accepting one. Okay, so with this we can see that we have two different types of automata, of pushdown automata. Okay, in this case we have an automaton which is non-deterministic, and accepts this language here. But this language cannot be accepted by a deterministic automaton, because imagine that we have a word like, for instance, a very simple word like, for instance, 00. Of course, this word must be accepted by the automaton. Imagine that we have a deterministic automaton that is working by empty stack, and it reads this word. Then after reading 00, this is in the language, so it must empty the stack and accept. Okay? So after this step, the stack must be empty. But imagine that I have this word, 4 consecutive zeros. If here I empty the stack after the second symbol, then it is impossible to read the rest of the word, and this word won't be accepted although it is in the language. Okay, so this is a problem with deterministic finite automata for this language, because if they accept the first word, they must empty the stack. But then they empty the stack at this point and they do not accept this word. So there is no deterministic pushdown automaton that is able to accept this language here. Okay, so the power of the deterministic and non-deterministic pushdown automaton is different. Okay, in the first case, when we have deterministic, non-deterministic finite automata, then we can analyze, it is possible to accept all the context-free languages. It is possible to accept all the context-free languages. In the case of deterministic automata, it is only possible for certain languages. It is, of course, a large subset of the context-free languages, but is not the set of all the context-free languages. So if we are looking for a machine model that is equivalent to context-free languages, then we need to choose non-deterministic pushdown automaton and not just deterministic automata, because then we are not able to recognize, to accept all the languages. Okay, notice also that in the case of non-determinism, we have here backtracking. Okay, because we have several different branches and we need to explore all of them. Okay, and this makes this type of automata non-efficient. However, when we have deterministic finite pushdown automata, then we have no backtracking. We have always just one possibility after a given situation, and then we can make this computation efficient. Okay, so they are different in power and they are also different in efficiency. Okay, but for us, the important the important type of pushdown automata is the non-deterministic pushdown automata, because they are the ones that are equivalent to context-free grammars. Okay, and of course that is the other open question that we have to solve before we finish this unit, is how to show that pushdown automata, non-deterministic pushdown automata, are equivalent to context-free grammars. Okay, this is exactly the content of this theorem here, and we are only going to prove one of the directions of this theorem. We are going to prove that whenever we have a context-free grammar, then we can obtain very easily pushdown automaton that is equivalent. And the other direction is also provable, But we are not going to study the algorithm to transform a pushdown automaton into a context-free grammar. If you are interested in that construction, then you can check the book by Hofgrove, Ullman, and Motwani, and it's explained there. If you have an interest in that construction, please read it in the book and ask me or ask me to clarify any question that you may have, or ask me for a pointer to and other places in which you can read about that transformation. We are going to focus only on the transformation from um, pushdown out from grammar to pushdown automata. Okay, and the idea is that we are going to use the stack in the pushdown automaton to reproduce the different derivations that we can have in the grammar. Okay, so we are kind of brute forcing the search for a leftmost derivation of the string that we have in the tape. Okay, so we are going to start with the axiom, with the start variable of the grammar. We are going to use non-deterministically the stack in order to generate um, all the possible derivations starting from the initial variable, and we are going to check whether at least one of those derivations is producing exactly the word that we have in the tape. Okay, so let me give you an example. Here, imagine that we have this grammar with these productions here. Okay, and we want to study whether um, this word is generated by the grammar. Okay, of course we know that it is generated because here we have a derivation of the word in the grammar, but we want to check that with the pushdown automaton. Okay, so what we are going to do is to start in the automaton with the initial variable of the automaton, and then notice that this is the first step in the derivation, and then we are going to use the stack in order to reproduce the derivation of the word in the grammar. Okay, so notice that what we do is to always substitute the symbol that is at the top of the grammar of the stack with something that can be generated from that variable. Okay, so here for instance we have a production which is A produces A B. Let's go back to the grammar and notice that here we have this production. So that is what we are using here in the stack of the pushdown automaton. We are checking what is the variable that is at the top, and then we are substituting that variable with something that can be produced from the variable. In this case, the string AAB. Okay. Now we have a terminal at the top of the grammar, and then we check whether that terminal is the first symbol in the word that we want to generate. Okay, and in that case we move to a situation in which we have read the symbol on the tape and we eliminate the symbol from the top of the stack. Okay, now again we find a variable at the top of the stack, and we use this production here in order to substitute the variable with the string that it produces. Okay? Again, we check this terminal against the symbol that we have on the tape. We eliminate both, and now we find again a variable at the top of the stack. In this case, we are going to use another of the productions that we have in the grammar, which is A produces lambda. This is another possibility that we had here for variable A. And then what we do is to remove that A from the stack. We substitute A with lambda. Okay? Now we have a symbol which is a terminal at the top of the stack, which is exactly the same that we have on the tape. So we eliminate both. Again, a symbol at the top of the stack that is exactly what we have on the tape, so we can eliminate both. And then we find a variable at the top of the stack. In this case, we are going to use the production B produces CB, which is another of the productions in the grammar, this one here. Okay, so we get CB, and the C is exactly the symbol that we have on the tape, and then we find B, which we substitute with another production, in this case for lambda, and then we empty the stack and we have read the complete word, and then we accept. Okay, so what we are doing here, if you notice, is that we are reproducing what we do in the derivation, but in the stack of the automaton. Here we have AB, and in the stack we have AB. Here AABB. That's the same that at this step in the stack. Here AAABBB, but we have already canceled this first A, and so on. Okay, so at the end we are reproducing the derivation of the string in the grammar, but we are doing it with the stack of the pushdown automaton. Okay, so this is an example of a general construction which is given by this simple algorithm. When we have a grammar and we want to generate a pushdown automaton that is equivalent to it, that accepts exactly the language generated by the grammar, what we do is to use as alphabet, of course, the set of terminals of the grammar. Okay? In the stack, we are going to reproduce the derivation, so we need as alphabet of the stack both the variables and the terminals. Okay, because we are going to use the stack to reproduce a derivation, and in a derivation we can have both variables and terminals. The initial symbol of the stack is the axiom of the grammar, because any derivation starts with the initial variable, with the axiom of the grammar. And notice that we only have one state. We don't use the states, we use the stack to do everything. Okay, and we are going to work by empty stacks. We want to check whether at the end the stack is empty or not, so we do not need to specify what are the accepting states, because we don't need them. Okay, and of course, since we have only one state, that is the initial state. And then the transitions are very easy. We add a transition for the situation in which we find the same symbol, the same terminal on the tape and on the top of the stack, in that situation we just pop the symbol from the stack. Okay, we read the symbol from the tape and we pop the symbol from the stack. This is a transition in which we find that one of the symbols on the string has already been produced on the stack, so we are in a situation in which we can be sure that at least one of the symbols is produced, so we can remove it and see if the rest of the symbols are produced or not. Okay, and the other situation is when we have one variable at the top of the stack, and in that situation, without reading anything from the tape, we substitute A with alpha, where alpha is something that can be produced from A on the grammar. Okay, so that is exactly what we were doing with the previous example. So we have two types of transitions, two types of movements. This first type of movement is one in which we read a symbol from the tape and we pop the same symbol from the top of the stack. And the second type of transition is a transition in which we substitute a variable from the stack with something that is produced by that variable in the grammar. Okay, so here you have an example of how to do this for a grammar that you are familiar with, because it's the one that you use on in the lab to check for arithmetic expressions. But let me give you an example which is a little bit easier. Okay, so let's remember about the grammar that we used to generate the words of the form a to the power n, b to the power n. Okay, it's this grammar here. So what's the equivalent push-down automaton in this case? Notice that we have two terminals. The terminals here are a and b, and only one variable. The variable here is s. Okay, so the transitions are of two types. First, we have transitions for the symbols in the terminals, in the set of terminals, which are always of this form. We always pop the symbol from the tape, from the stack. So we have that transition for A and that transition for B. And then for the variables, we always have lambda movements in which when we find S on top of the stack, we substitute S with any of the things that can be generated from the variable. In this case, we can generate ASB or lambda, so we have two possibilities. Either we substitute S with SAB, or we substitute S with lambda. Okay, so this is very easy because we just rewrite the grammar in a different way. We have one transition for each of the terminals and one transition for each of the variables. The transitions for the terminals are always just to pop the terminal from the stack, and the transitions for the variables are to substitute the variable with any of the productions of that variable in the grammar. And that's all that we need to do. Okay, so this is the end of lecture of this lecture, and this the end of the second unit. Remember that on Friday at 11 a.m. we are going to have a Microsoft Teams meeting in which you can ask me any question about this unit. And I have also uploaded to the virtual campus an example of a test from previous years. So if we have time after your questions, I'm going to solve some of the exercises in that exam so you can see how to solve them. Okay, so if you want to take a look at the exam and you want to ask me to solve some of the exercises, some of those that you are more interested in, that's of course uh, very interesting. Okay, so please take a look at the exam if you want to and ask me anything that you uh, want about the exam or about this unit on our meeting on Friday. Thank you very much, and we'll meet again on Friday.